All right, you guys, let's wrap up chapter 6 with this lesson on partial fractions, which I think are super fun, and improper intervals. Okay? Okay, so it starts about like, think back to your Algebra 1 days, right? It says, we've often simplified an expression like 1 over x minus 4 minus 1 over x minus 3 by getting a common denominator and combining them into 1. Okay, do not worry about writing this down. Let's just make sure that you guys remember how to do this. You guys remember that we would get a common denominator by multiplying that by x minus 3 and then multiplying that by x minus 4. So the denominator was x minus 3, x minus 4, and on the top I would get 1x minus 3 minus 1x plus 4, and I would end up getting like 1 over x minus 4, x minus 3. Okay? I am going to teach you a way to take that and go backwards, right? Now, what's the purpose of that? Why would we want to do that? Well, it's because we can split a fraction up to make integration easier, right? Right here, I can't split that up, okay? I can't split that up. But if I could split it up with what's called partial fractions, I can integrate it better. So let's like kind of take a look. This is this same idea of what we're just doing up here, combining like terms, but we're like separating them. Okay, and here's how it works. This is very algebra heavy, so hopefully you're feeling good about your algebra. All right, so right now I'm gonna take this and say, I want to separate this into two separate fractions. Now this is x minus 3, x minus 4. So I don't know what numbers are going to go on the top, but what I do is I go, okay, it's something over x minus 3 and something over x minus 4. Okay? Because it's the reverse process of putting two fractions, getting common denominator and putting together. It's taking them apart. Now let's go ahead and work with this equation really quick. Okay, so in order to get rid of the fractions, well, basically what I want to do is if I can, this is x minus 3, x minus 4, so I can get all these to match if this is x minus 4 on the top and bottom, and then I put x minus 3 on the top and bottom. Okay, so do you guys see how this term, and this term are all identical terms? And so what we can do is we can take and make this equation right here. All right. And at that point, we can use like a system of equations or something to solve this. But there's a longer way of solving it, and there's a faster way of solving it. Okay. Now let me show you like this really. It's just this little trick. It's this little method that's like a fast way of solving it. The first thing I'm going to do is say pretend x is 4. Now why would I do that? Well, when I go to plug this in, do you guys see that 4 minus 4 is 0? And so this whole thing would cross off. Okay? So 1 is b times 4 minus 3. So b is 1. So I just solve for b. So that's cool. Now let's say I let x equal 3. Why am I doing that? Well, if I go to plug that in, so I have 1 equals a, and that's 3 minus 4, and then b, and that's 3 minus 3, then guess what? This time, that's 0, and the b cancels out. So a times negative 1 is 1. So a is negative 1. So that just solved my partial fractions. So go back to the beginning. Remember that before I had done all this, I said, well, I could split this up to a over x minus 3 and b over x minus 4. Okay? Now, I just found out that a was negative 1 and b was positive 1. Okay? And these should both have a dx on them. And now that I did this, like, again, guys, this is all algebra stuff. Now that I did all that, I can integrate this, right? I can go, okay, this is -1, and then it's an ln, right? It's kind of like u sub, but you don't really have to necessarily do u sub because it's just a 1x right there, so it's fine. So that's an ln. This is also an ln. There's my answer. All right? One thing I want you to notice is that on a multiple choice test, it's possible this answer might be written like this. Okay, it might be. Do you guys see that? Because remember when we subtract ln's, we're really dividing. And so if I do that ln minus that ln, we can put it together and divide. So you might see that. This is what we could do with like ln properties. On a free response, we would just leave it like the first way I wrote it. Okay? So that's a method called partial fractions. So how do we know when we use partial fractions? All right, well, what I can do for this question is I can actually, okay, I can go like this. Hold on one sec. Okay, I'm going to separate this out. That's -3 plus 1. And I get, okay, if I'm separating this out, a over x minus 3, b over x plus 1 equals 5x minus 3 over x minus 3, x plus 1. Okay, there's my partial fraction. And let me see if I can find a and b. All right. This I would need to multiply by x plus 1 on the top and bottom. This I would need to multiply by x minus 3 on the top and bottom. And I end up, again, see how that, and that are all equal to each other? So I end up just having this equation right here. Okay? So that equation is a times x plus 1, b times x minus 3 equals 5x minus 3. And again, I'm going to use this little trick. Like, so algebraically, I could try to like multiply this out and set the x's equal and stuff, but there's just a little trick you can do. You go, well, first I'm going to let x equal what? Well, how do I make that 0? Let x equal -1. Okay? If x is -1, I have a times 0 plus b times -4 equals 5 times -1 minus 3. So b times -4 equals -8, so b is 2. Then for the second part, I go, how would I make that 0? Well, let's let x equal 3. And now I go, okay, a and 3 plus 1 is 4. B and 3 minus 3 is 0. And that equals 5 times 3 minus 3. So a times 4 is 15 minus 3. So that's 12. A is 3. Okay? So I can rewrite now my integral as, this one was x minus 3. This one was x plus 1. And a was 3. That was the number above here. And b is 2. And now, you guys, the integral is actually pretty easy. Okay? Because it's 3 ln of that and 2 ln of that. Okay? Okay, nice. Let's go down here. Don't assume that everything that you do is going to be partial fractions. Don't just immediately be like, oh, good, I'm going to do a partial fraction, right? Now, up here, here's what happened. Look, I had to do a partial fraction on this because if I tried to do u sub on this question, my du is 2x minus 2, which is not that, and I can't turn it into that. And so that's why I had to do a partial fraction, okay? Okay, over here, if u is x squared minus 2x minus 3, du is 2x minus 2, and it's perfect. This is absolutely perfect because it just ends up being 1 over u du, which is ln of u, all right? So it's like ln of x squared minus 2x minus 3 plus c. You're probably going to be like, well, gosh, dang, how would I look at those and see? I mean, you just have to get used to these problems, you know? That one of them is u sub and one's partial fractions. It's really hard to tell because they both have the exact same thing on the bottom and they both have a linear term on the top. You just got to try something. If it doesn't work, try something else. Okay? Okay, let's see. With example 4, I think I'm going to go ahead and start with long division. Okay, which is what I could do when I have like a polynomial. I'm saving a little space there for the x squared. Alright, I'm going to do long division to separate this one out. Okay, so the first thing I'm going to do is x. Now when I multiply that down, I get x to the third plus x squared minus 2x. I change the signs, minus minus plus. Okay, and I get negative x squared, and negative x plus 2x is plus x plus 2. Alright, now how many times does x squared go into negative x squared? Negative 1 time. And when I multiply that, I get negative x squared minus x plus 2. Change the signs, and I end up getting 2x right here. Okay? So step 1, by long division, this went to x minus 1, and then a remainder of 2x over this. Okay? Now, this is going to be very easy to integrate. This is going to be very easy to integrate. This is a little harder to integrate. So let's see what that is, and let me just do that entire problem off over here, okay? So first, maybe I would try u sub, and I'm like, okay, if u is x squared plus x minus 2, du is 2x plus 1 dx. But that doesn't work because of the plus 1. So I'm like, all right, u sub does not work. What else? Long division. I can't do long division when the bottom's bigger than the top. Alright, the top has to be bigger than the bottom or equal to do long division. So I'm going to try partial fractions, right? Especially a big clue of when you're going to try partial fractions is when this bottom part factors out. X plus 2x minus 1. So this fraction is 2x over x plus 2x minus 1. And I want to make it a over x plus 2, b over x minus 1. Okay? Multiply everything to get a common denominator. So I need an x minus 1 on here, and an x plus 2 on here. So I notice that, and that are the same. So I'm going to grab this equation right here. I'm going to go, okay, 2x is a times x minus 1, and b times x plus 2. And then I'm going to go, let x equal something to get rid of the a, let x equal something to get rid of the b. So see if you guys can do that. Pause the video real quick maybe and see if you can find a and b algebraically, okay? Okay, so for this first one, if x is 1, I ended up getting 2 times 1 equals, that's going to go to 0, a times 0, and b times 3. So 2 equals b times 3, so b is 2/3. For the next one, I'm going to let x equals negative 2. And so I get 2 times negative 2 is a times negative 3, and b times 0. So negative 4 equals a times negative 3, so a is 4/3. Okay, so my a and b are 2/3 and 4/3. Alright, remember what the heck we were trying to do in the first place. I'm going to go back over to here, and I'm integrating a over x plus 2 and b over x minus 1, okay? And so you guys, here's my final answer, alright? Okay, I've got x squared over 2 minus x. This then turns into an ln, so it's 4/3 ln x plus 2 this also turns into an ln. 2/3 ln x minus 1 plus c. Okay? That's kind of is like how complicated the partial fractions would get. Cool. Alright, I love it. Alright. Last little part of this section and the last kind of topic of integrals that we're going to talk about are improper integrals, right? An integral is called improper if one of two things happen. One or both limits are infinite, okay? So this is, why is it improper? It has an infinite limit, right? It says, why is this improper? It has two infinite limits. All right, so that's the reasoning. It just wants to know why they're improper, so that's what it would look like, okay? Or if it has an infinite discontinuity, basically, you guys, if it has a vertical asymptote at or between the limits. All right, now look at number 7. This has, if I said that equal to 0, x equals 1 is a vertical asymptote, and that's at one of the limits. So why is this one improper? Because it has a vertical asymptote at x equals 1, which is one of the limits. Now, why is this one improper? Well, this one has a vertical asymptote at -1. And if you look at this, -1 is smack dab in between there. So there's a vertical asymptote at -1, which is between the limits, so on this one, it is the lower limit, so you can't do that. This one is between the limits. Okay, hopefully any of these, well, you can't really type the infinity thing into your calculator, but the other ones, it should hopefully not give me an answer. So like number 8, for example, let's say I'm going to type this into my calculator, okay? And I go math 9, and I go from -2 to 2. Hopefully it won't work because it's not supposed to. All right, -2 to 2 of fraction 1 over x plus 1 squared dx. Okay? And it gives me an error. And the reason, well, if you wanted to look up here, I guess, in my y equals, let me clear out from there. If we wanted to look at this in y equals, all right, it's because if I do 1 over x plus 1 squared, okay, so you guys see that? And so if I'm trying to calculate the integral from -2 to 2, it's not going to like that, okay? It's not going to let me. Now, what if I wanted to calculate the integral from -4 to -2? That's fine. It'll calculate that because it's not going over the asymptote. You just can't go past the asymptote. Okay? Okay, now, some of these things, though, they actually do, you can figure them out. They can converge or they can diverge. Now, this is a little bit weird because, okay, as it's going to infinity, let's take a look at number 9 and 10. Now, you can't actually evaluate with an infinity in here. Like, it just doesn't really work like that. So here's what we have to do. We have to say, okay, I'm actually going to take the limit as x. Well, I'm not going to use x. There's already an x in there. Let's use a different letter. Let's use b. As b approaches infinity from 1 to b of this. So you can't, this is like more of a formal writing up. Would you have to formally write this up if you were on a multiple choice section? Absolutely not. This is formal writing up of this for response or something, right? So it's the limit as b approaches infinity of, now x to the -2, let me just write this over here, is x to the -1 over -1. And so it's going to be -1 over x, okay, evaluated from b to 1. And then remember, when we evaluate, we do top minus bottom. And so I end up getting in here negative 1 over b minus negative 1 over 1. Okay? So it's the limit as b approaches infinity, negative 1 over b plus 1. Now, can we evaluate that as b goes to infinity? Well, 1 over infinity, 1 over an infinitely large number, ends up just being 0. So I can evaluate this. So this is what's called, it converges, and I can actually get an answer. Okay? Now, I can't really show you on your calculator. You can't really go to infinity, but check this out. All right, let's just make this 1 over x squared, so I can do that by just deleting this and this. Okay, there's what my graph looks like. Let's calculate the integral from 1 to a very large number. Let's go to like 100. Nope, too large. Let's try to calculate 1 to 10. Calculate an integral from 1 to 10. 10 is not a very large number, but it gives me 0.9. And as I get bigger and bigger and bigger, it's going to get closer and closer to 1. Let's do it over here. Let's go integral from 1. Let's see if it'll do it. I don't know. Maybe I'll just try going to like 50 or something. Of 1 over x squared dx. Ah, nice. Not bad. Let's see if it'll get closer than 50. Let's see if it'll do 100. I don't know. Might get mad at me, but we'll see. Ah, let's go. Okay. Let's see if we can do 500. Ooh, even closer, right? So, I mean, we can do this all day, guys. You just put a 0 on here and see if it'll do 5,000. Hey, even closer. Okay, so as we go, you can see that that limit is approaching 1. So that's why we say that this converges. Now, let's do the same process with this next one. All right? Okay. So this one, we're going to go, all right, the limit as b approaches infinity, 1 to b of 1 over x dx. Well, I need to integrate that. And the integral of 1 over x is ln of x, and I'm evaluating it from b to 1. Okay? And when I plug that in, I get ln of b minus ln of 1. Now, if you guys remember, we know that the ln of 1 is 0. Okay? So this is just the ln of a very, very, very large number. And the ln of infinity basically still goes to infinity. So we say that this one diverges. Even though these look so similar, number 10 doesn't have an answer because it just keeps going up to infinity. Okay? Okay, so let's see if cosine converges or diverges. So again, we don't want to work with the infinity in there. We want to write, okay, limit as I approach infinity. And I want to do integral of cosine of sine. Oh, well, first let me check this out. Integral of cosine x from 0 to b. Now I can actually do this. Okay, so it's the limit as b approaches infinity. The integral of cosine is sine, evaluated b to 0. And in here I end up getting sine b minus sine 0. Okay, well, the sine of 0 is 0. Now, as b goes to infinity, does that settle down? Well, no, because sine, it just keeps going like this forever and ever and ever. So it's oscillating, and it oscillates forever. So that, we don't have a limit as b approaches that, so this diverges. Okay, we do not have a limit as b approaches infinity for sine, because it just keeps straight going up and down, up and down, up and down. Okay? Cool. All right, here we go. Limit as we approach infinity, 1 to b of this. Now let's see, let's run through what we know. This is not a U sub problem. This is not partial fractions because it's not like a fraction thing. This is, yeah, what could it be? It's kind of like the thing where we do product rule and we go backwards. You guys remember what we did for that? Ultraviolet voodoo. This is an integration by parts. Okay? Well, remember, we start by saying let u equal something and dv equal something. Okay? And I believe in this case we wanted to let u be x and dv be e to the negative x, because then du is 1 dx. No, that is dx on it. And v, if I go backwards, okay, the integral of e to the negative x is e to the negative x with a negative. Okay? This is an ultraviolet voodoo problem. So, limit as b goes to infinity of, okay, so it's uv minus v du. Okay? Ultraviolet voodoo. Let's wait a minute on that limit. Let's just go. Okay, so this is negative x e to the negative x plus the integral of e to the negative x is e to the negative x with another negative, so now it goes back to minus. Okay? We're evaluating it from b to 1, limit as b approaches infinity. So if I were to do negative b e to the negative b minus e to the negative b, and negative 1 e to the negative 1 minus e to the negative 1. Okay, couple things I would like you to remember. The limit as b goes to infinity. So let's think about this. What's the limit as b goes to infinity of e to the negative b? Well, another way of writing e to the negative b is 1 over e to the b. And if that's going to infinity, 1 over infinity is 0. So anywhere I see an e to the negative b, that's a 0, that's a 0. Okay? So this is going to be 0 minus 0. And then it'll be negative 1 over e minus 1 over e. So it looks like it's negative 2 over e. Okay? And so this one converges and it looks like we get 2 over e for our value. And if we plug this in and we did bigger and bigger and bigger values, we should eventually get to 2 over e. Okay, and the last one. I mean, I would, okay, well, first thing that you have to notice here is this has an asymptote at 0. Now, it is still possible that this thing has a limit that converges. It's something weird's happening, but I could possibly split it up and just see, okay? That's 1 over x to the third dx, and then that's 1 over x to the third dx. So I'm going to split it up, and I'm going to see what happens. All right? But we have this asymptote here. Now, this graph, 1 over x to the third, let's like take a look, just so you guys can see what we're looking at here. Okay, so fraction 1 over x to the third. All right? And so what we're going to do is we're going to take the left-hand limit. So basically we're going to approach 0 from the left. So limit as I approach 0 from the left. Okay. And then we're going to do on this side, limit as I approach 0 from the right. This time I'm going to use a, because like, you know, my integrals go a to b. And then it's a to 2 of that. Okay? So I've got these like 2 separate limits here. These 2 separate statements. Now, Okay, real quick, just so I only have to do it once. The integral of x to negative 3 is x to negative 2 over negative 2. So it's basically, okay, let's see, negative 1/2 and then an x squared on the bottom. And then this one is, same thing, negative 1 over 2x squared, evaluated 2 to a. Okay. And then we write, okay, so then we do top minus bottom, so it's negative 1 over 2b squared minus negative 1/2. But as I'm approaching 0, this one also is just going to be, like, this one's not going to work, okay? Because a number over 0, right? So this diverges. Same thing over here. It's like, if I did this, I would get, okay, it'd be negative 1 over 2 times 2 squared, so 2 times 4 is 8, minus negative 1 over 2a squared. The limit as a is approaching 0 from the right. But again, as that's approaching 0, that also diverges. So I'm not going to be able to figure this out. Okay? So those are improper integral proofs. So much fun. Right around 30 minutes. Let's go.